Greetings and good morning or good afternoon, depending on where you are. My name is Professor Duke Orata. We are continuing with our lectures. We're still looking at radiation. Remember, we talked about black body, and we said this is a body which absorbs every radiation incident upon its surface. So that basically, we are saying that absorptivity, which is the ratio of the energy absorbed to that of the total incident energy, we said it was 1 in the case of black body. And we are continuing with our discussions. 1, when you're talking about emission of radiations, we are talking about emission of electromagnetic waves. So we are still on radiation. Involves emission of electromagnetic waves. And what is the import of this? These waves have a wavelength, and these waves are related to frequencies, to frequency, which is always in cycles per second. These waves are related to frequency in cycles per second in terms of their wavelength. That is, the frequency of the waves is given by the expression V is equals to C over lambda. In other words, each of these waves has a different frequency, which is related to the speed of propagation of that wave and its wavelength, where C is the speed of propagation and lambda is the wavelength. So that V normally is in cycles per second, but if wavelength is in meters, then C will be 3 times 10 to the power 8 meters per second. That's the speed of propagation of that particular wave. And so this is very, very important. This is important. In other words, it brings us to the concept of monochromatic absorptivity, which means that this absorption of that particular radiation is related to the waveband and to the angle of incidence. Monochromatic is related to the waveband and angle of incidence. Therefore, what does that mean? It means that when we're talking of monochromatic absorptivity, we are talking of the ratio. We are talking of a ratio of the energy which is absorbed within that waveband and angle and the solid angle dW divided by the total incident energy in that waveband and that solid angle. So we are talking of the ratio energy absorbed angle and solid angle d omega. Similarly, monochromatic emissivity also deals with the energy emitted from this waveband and solid angle. To that, which of course, the incident energy in that waveband and solid angle. So monochromatic also is related energy emitted band, K lambda, and solid angle, UW. And so those are ratios. Energy absorbed within the wave band and that solid angle to the total incident energy in that wave band and solid angle and so forth for monochromatic emissivity. Now, in a nutshell, what are we saying? In a nutshell, what are we saying? We are saying that that energy is related to Q, black body at that wave band and the wavelength. And this QB lambda is what we call the monochromatic emissive power. Refer to that as monochromatic emissive power. And so when we are talking about hemispherical emissivity, that's over the hemisphere, talking about the hemispherical emissivity, that's over the whole hemisphere, that will be given by the ratio of the emitted radiation that emitted by a black body at the same temperature. Now, these are very important concepts because remember now we have put this kind of a caveat. There is this kind of a selection rule. In other words, that we are talking of radiation absorbed within a certain energy band and at a certain angle of incidence. That means now we are talking about selectivity. And so, what does that mean? Remember that this monochromatic emissive power, Q, Bx, has its spectral distribution. And this is described by what we call by Planck's law. And what is that? It says that the spectral distribution of this monochromatic emissive power is C1 to the minus pi, C2 over lambda t minus 1, and C1, these are constants, and C2 are constants. And of course, when you differentiate this quantity here, you end up with the expression. So on differentiation, we end up with the expression 0.002. And this is an expression which you can use to calculate the lambda max. And that lambda max profile, clearly, that lambda max profile, we have the monochromatic emissive power, the wavelength, then you're going to see that the lambda max is decreasing with increasing temperature, decreasing with increasing temperature in general. You see that the lambda max, this lambda max, is decreasing with increasing temperature. So these are very important quantities which we need to know. Now, not all bodies behave like black body, but there's a body which behaves like an ideal body, where most of the materials approach its behavior. So most of the materials do not behave like the black body. What do we mean by that? All we mean is that most of the materials don't obey the radiation laws of black body. Maybe you might get platinum black. Examples which obey that is just platinum black, among some of those which obey the black body material. But there's another body. Which is called a gray body. A gray body. There's another ideal body. Whose radiation laws are in agreement with most materials, and we call it the gray body. And one characteristic of the gray body is that its monochromatic absorptivity is constant, does not depend on the wave band. The gray body, monochromatic absorptivity is constant. Therefore, does not depend on wavelength. It does not depend on wavelength. It does not depend on wavelength. In terms of the gray body. And of course, it does not depend on wavelength. Naturally, it doesn't depend on angle of incidence. Then we'll have to note that. Now, but those bodies which you are talking about, when you're talking of those bodies, whose monochromatic absorptivity depends on lambda and phi, that is the wave band and the angle of incidence, those bodies are called selective emitters. Depend on lambda and phi are selective emitters. So that if you have your plot, these selective emitters, for the black body, you have that, but for the selective emitters, you have something like that. It's for black body, and this is a case of selective emitters. In a nutshell, very simple. This depends on lambda and the angle of incidence, the wave band and the angle of incidence. So they're selective emitters, but the black body does not. The black body does not. The gray body has a constant monochromatic absorptivity. In other words, it doesn't depend on lambda and it doesn't depend on angle of incidence. So all these concepts are coined in an important law which we call Kirchoff's law. Kirchoff's law, which says that the monochromatic emissivity of a surface 1 at some temperature 1 is equals to its monochromatic absorptivity of radiation from a surface 2 at temperature T2, where T1 is equals to T2. The monochromatic emissivity of a surface, one at temperature T1 is equal to the monochromatic absorptivity of radiation from a surface to at temperature T2, where T1 is equal to T2. We can say that the emissivity, in a nutshell, is equal to the absorptivity where temperature T1 is equal to T2. Very important, that is Kirchhoff's law. So that's a very, very important observation in terms of these selectivities involving wave bands and the solid angle. So let's stop at this particular point. We are continuing with these lectures.